Alright, so in this lesson we're going to start looking at the idea of moment of inertia and what this actually tells us about rotating objects. So what moment of inertia really is it's a mathematical way to account for the effect of mass in a rotating object. And if I have a set of particles, the easiest way to calculate moment of inertia is to take the mass of the particle and multiply by the distance between that particle and whatever your axis of rotation is, what I call r. And so you take mr squared for each individual particle, add all those values up, and you get the moment of inertia of that object or that system of particles. So it works pretty well for a system of particles. It looks really similar to center of mass for a system of particles. Where this becomes harder is if you have an object that is not a discrete set of particles, but rather a mixture or a distribution of particles or a distribution of mass. Now there are some ways to deal with uniform distributions of masses, and here I have kind of 9 common situations or 9 common places or ways that you could have a mass uniformly distributed about an axis. The one thing to point out about all of these situations is that there's some sort of symmetry about this. Either the axis is through the center of the hoop, or through the center of a solid cylinder, or through the center of a square slab of material or rectangular slab of material. If we start to deal with distributions of masses which are not what I would call uniform, we run into other problems. We will look at later on a technique to deal with non-uniform distributions of masses. There is a way to deal with that using some calculus. We'll also prove that some of these statements are true. We'll also look at another way to deal with a situation here later on where the axis of rotation is not through, say, the center of the hoop. What do we deal with? How do we deal with that situation? There happens to be a very, very easy way to deal with certain types of situations called the parallel axis theorem, which is if you have an axis parallel to one of these axes, you can then derive a moment of inertia about that axis by knowing what the moment of inertia about, say, the axis about the center of the hoop is. So maybe an example is maybe instead of an axis through the center of the hoop, maybe it's on a point on the outside and the hoop is rotating about that point. We can actually come up with a way to calculate moment of inertia in that situation dealing with parallel axis theorem. We'll talk about that in a few lessons from now. So let's look at a quick problem dealing with the moment of inertia of an object. And here we have a rod, and the rod has a mass of 2m and a length L. And it has 2 balls glued to each end of the rod, each with a mass m. And so I want to determine, in terms of m and L, what is the moment of inertia of this rod. And it says the axis of rotation is through the midpoint of the rod. So in order to calculate the moment of inertia, I would calculate the moment of inertia of the rod and add the moment of inertia of the 2 balls. And that'd be the total moment of inertia of the system. So worth pointing out, if we remove the balls, the moment of inertia decreases in this case. If we added bigger balls to each side, the moment of inertia would get bigger. So the way to do this, we have a rod with the moment of inertia in the middle. It happens to be 1/12 mass of the rod times length of the rod squared. And then we're going to look at each ball is at a distance of L over 2 from the axis of rotation. Each one has a mass of m. There are 2 of them, so 2m basically r squared. And so if we actually work this out, we find that the moment of inertia of this system is 2/3 ml squared, where m is the mass of, well, a ball basically, and L is the length of the rod. So some things that would make this moment of inertia bigger is if you had longer rods or larger masses. Now what happens if we flip this, and instead of having it be on the outside of one, maybe we have it on the far left side. So this means the moment of inertia of the ball on the left side is actually 0 because it is at that location. So we're going to do moment of inertia of the rod plus moment of inertia of the right side ball. And if you look up what the moment of inertia of a rod is rotating about one end of the rod, it's actually 1/3 mass of the rod times length squared. So it actually quadruples the moment of inertia to move from the center to one of the ends, which makes sense. We'll prove that that makes sense when we get to parallel axis theorem or dealing with another way to calculate moment of inertia. And we have ml squared. So if we actually work this out, it actually ends up being 5/3 ml squared. So we increase the moment of inertia by changing where that axis is. It would happen to work out if the axis was on the far right side, we would end up with the same answer based upon the symmetry of this system. So that's how we calculate moment of inertia. Lots of times we come across one of these systems where it is clear or something that you can easily calculate what the moment of inertia of a system is. When we look at our other technique to calculate moment of inertia later on in the year using some calculus, we might be given other pieces of information that we could use to calculate I given the distribution of a mass. So that's kind of a quick overview of moment of inertia. Where this becomes helpful is it gets used in rotational kinetic energy, rotational dynamics, Newton's second law for torque, and angular momentum all relate back to moment of inertia.